Hello, my name is Allan, and today I'll be talking about three time domain EEG metrics in our group's beginning explorations into their potential connection to the system factorial technology methodology detailed in Townsend Nozawa in 1995. I want to first talk about the behavioral paradigm our lab used to study perception architecture using response time distributions analyzed within the system factorial technology. As part of her dissertation, Gao-Jifan collected data from a detection task using Gabor patches containing two components: a high-frequency grading oriented at 45 degrees and a low-frequency grading oriented at 135 degrees. When present, salience of each grading was manipulated across two levels of luminance contrast. Across sessions, observers completed two task types: an AND task in which the observer indicated yes only if both components appeared, and an OR task in which observers indicated if any component was present. In addition, motivation by an extension of the theoretical methodology presented in Thomas, Fawn, and Gamble in 2019, the Gabor patch could appear in either the left visual field, right visual field, or in both. For this beginning exploration, we examined the data from one observer, observer 5, in the OR task and in the bilateral visual field condition, which represents the extension of SFT to nested architectures. This observer was one of only two to complete all sessions in the experiment. One open question concerns how to relate measures of neural activity to reaction time methods of SFT. The literature suggests three time domain EEG measures that could serve as a proxy for the hidden cognitive processes indirectly assessed by reaction time. First, Nunez and colleagues proposed an N200 derived from the singular value decomposition algorithm as a potential measure of the visual encoding time. In their 2017 and 2019 papers, they found a correlation between aspects of the N200 encoding time and the drift rate from the drift diffusion model. This figure from the 2019 paper shows how this type of N200 waveform should behave. Secondly, the central parietal positivity, typically measured at the parietal midline location, has been proposed as a neural correlate of evidence accumulation. In various different papers, the CPP peak amplitude and latency correlates with reaction time, and changes in amplitude tracks discrimination difficulty. From these early studies, researchers have hypothesized that CPP may be the signature of the evidence accumulation process at the heart of the diffusion decision model. In Tagliabue and colleagues' 2018 article, they show what a good CPP waveform should look like by slowly increasing to its peak around 300 milliseconds. Lastly, we have the long-studied lateralized readiness potential, both the stimulus and response locked variants. In a review on the LRP, Smulders and Miller in 2012 suggested overall response times could be partitioned into stimulus categorization time plus response execution time by measuring the latency of stimulus-locked LRPs and the time between onset of response-locked LRP and reaction time, respectively. According to their partition hypothesis, overall reaction time is the sum of these two LRP latency measures. Recently, this idea has garnered support from the work by Van Voot and her colleagues in the computational modeling of perceptual decision. They reproduced the dynamic of LRP using a neural network model of the decision threshold crossing the diffusion framework. We begin by examining classical ERP waveforms that are often reviewed to determine if task difficulty or other decision parameters are being revealed in EEG dynamics. These include ERPs for channels P3, P4, and PZ. First, we see P3's ERP waveform, and it shows a steady increase, with local high, global high having a quicker starting point than local low, global low. Next, we see PZ, which shows a higher peak for local low, global low than its counterpart. And lastly, we see P4, which shows some very clean waveforms altogether. Lastly, we wanted to showcase some of the current findings and issues we have found in working through these metrics, while then looking at what we are doing to alleviate some of these issues moving into the immediate future. We can ask three specific questions seen here. With respect to the first question, unfortunately for this observer, we did not find this correlation. As can be seen, correlations were near zero and all p-values well above 0.1. With respect to the second question, interestingly, the SVD-derived N200 looked to be tracking stimulus salience. We await further data to investigate this more. We were perplexed with the absence of correlation between the EEG metric properties and overall reaction times. We believe that at least one or two choices in our processing pipeline may have obscured crucial structure in the trial-level data that render this result suspect. For example, we utilized an older form of ocular artifact correction that relied on regression techniques rather than a more modern approach using independent component analysis. We are also reviewing our computational algorithm for accuracy. Thank you very much for your time and for watching.